All right, good afternoon, everybody. Today's lecture will be on Deep Ontological Networks. The overview of today's lecture will be as seen here. First, a very brief introduction and motivation as provided by the authors of the paper. Then also a very brief background on what we call ontological reasoning, because it might not be in everybody's background. So we'll talk just a little bit about the semantic web and what we mean by ontologies, because it's the basis of what the authors develop in this work. Then we move on to the meat of the paper, which is recursive reasoning networks, the tool that they propose in this article. And we follow the same structure in this lecture as the authors do in the paper. I think it's very nicely done. First, they develop the problem statement itself, and then instead of getting right to the inner workings of the model, they provide intuitions about how they work, and then do a little bit of a deeper dive. In this case, we'll see that the actual guts of the model are quite straightforward in the sense that they don't develop anything very new. So they take recursive neural networks almost out of the box. They just do some clever encoding of the parts so that they encode ontological knowledge. So it's very, I think it's quite it's a good approach to do it in this fashion. And then to conclude, we'll see a little bit about how they evaluated their model and the results that they obtained on practical instances. So for introduction and motivation, the authors focus a lot on human-like reasoning. So as they pointed out as one of the major goals of AI, and they claim that machine learning approaches typically entertain a quite informal notion of reasoning, as it says here, which is often simply identified with a particular kind of prediction task. This is the kind of thing that we see typically in machine learning papers, right? They say, I'll be focusing on detecting this kind of object in this kind of media, like cats in pictures, or some sort of activity in a video. And that's then they solve the prediction task by getting new data, previously unseen data, and seeing how well the developed model or set of models or tools does on this previously unseen data. On the other side of the ring, typically we can see this as two opposite poles. We have knowledge representation and reasoning, typically called KR and R, or just KR, where these approaches typically take reasoning as the application of some kind of mathematical proof theory. For instance, as we've seen in this class, first order logic, or some kind of machinery of that kind. And it's also well known that each of these approaches has its upsides and its downsides, right? So machine learning, as we've seen in papers in the last few years especially, they get good results, sometimes very good results, great, on specific domains. They handle noise very well. When we say noise, we mean when you have some sort of unexpected aspect in the input, like a picture where you're trying to detect if there's a cat in the picture and a whole bunch of the pixels are dead, for instance, that kind of thing. The solutions are typically scalable, but on one of the worst aspects of these approaches is that they're brittle. When we say brittle, we mean that when you change something slightly, even the noise is one good example, because there's a lot of research nowadays in the last few years, especially on adversarial machine learning, where you just add noise that is especially crafted, so it's not something that randomly occurs in the environment, but it's especially crafted by an attacker, so that, for instance, you can change the prediction for a traffic sign, for instance, instead of predicting a stop sign when it's obviously a stop sign, you can craft some noise to add, and it will predict that it's some other kind of sign, like a yield or a speed limit sign. So on the other hand, KR is very expressive. It's correct in the sense that if you can do a derivation like you do in first order logic, there's no doubt that that's correct. It's flexible usually in their representations, but typically not that scalable, nothing compared to the kinds of things that we see in machine learning. And noise causes major issues. So for instance, there's a whole area in KR dedicated to reasoning under inconsistency. When you have a database and rules, and there's a problem, and there are problems inside the facts or the rules, and where constraints are not being met, and how do you answer queries? That's a whole area. And as we'll see in this lecture, this kind of thing is handled very well by machine learning approaches. So the authors propose recursive reasoning networks, as I was saying before, or RRNs, as a neuro symbolic model. And one of the questions that one might ask, and the authors themselves ask in the papers, why would somebody take a machine learning approach to reasoning? So that's also, we won't dedicate much to answer this question because it's one of the main issues that we're dealing with in this class. It's so combining machine learning and KR is now commonly regarded as one of the ways towards making significant progress in AI. So these approaches, as we've seen throughout the lectures, and we will continue seeing in the future, they are expected to allow leveraging background knowledge, for instance, to address the brittleness problem that we pointed out before, knowledge transfer. So when you have some kind of problem or set of problems already down, solved, how can you take advantage of that and solve a very similar problem? Learning from smaller amounts of data, one of the also downsides of machine learning is that they're very data hungry. And also, of course, in the last few years, we've heard a lot about explainability. So symbolic inference is typically regarded as being more adept to explaining, because you have these objects in your hand that you can point to and say how you inferred. But they might also help, these neurosymbolic approaches might also help make these neural models more explainable if the relationship between both sides is significant. So the goal, the authors point out, is to employ state-of-the-art techniques from deep learning to manage the balancing act, in their words, and obtain the best of both these worlds. So we'll start then with a very brief refresher on semantic web and ontological reasoning, as I promised. So the semantic web, quoting Tim Berners-Lee from his 2001, already over 2 decades old, Scientific American article, he says that the semantic web is not a separate web, but an extension of the current one, in which information is given well-defined meaning, better enabling computers and people to work in cooperation. So we can distinguish 3 key concepts here. He's talking about an extension of the normal quote-unquote web, or what we now call Web 1.0. We'll see a graphic example of this in a bit. Information needs to be given a well-defined meaning. That's why it's called a semantic web. So semantics is referring there to meaning. And the goal is to enable computers and people to cooperate. So trying to bridge this gap between, this large gap between machines and humans. So the semantic web aims to offer standards that help leverage semantics enriched data and knowledge at a large scale. So data with meaning, what do we mean by data with meaning? So a little bit of humor here. We can see what we say to dogs, and the owner presumably is talking to this dog, Ginger, and says, "I've had it, you stay out of the garbage," and says a whole bunch of things to the dog. And what the dog hears is, blah, 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 Ginger, only recognizes its name, right? And another from the same comic strip, Far Side, scientists trying to decode dolphin speak, and they're not doing very well. So this is kind of what we're up against when so the machines in this case would be the animals in the example. We're trying to communicate things through, sometimes to each other, but through machines, and we're not doing very well. So this is what the Web 1.1 looks like. So we have a graph, so that's why it's called the web, right? We have a resource, we have references between them, but this is what the computer sees. So it's understandable by us because we know what each one of these is. You can have natural language descriptions of them, you have documentation, you have all you want, but the computer can only read this. You say, oh, okay, from this resource I can jump to this, or there's some sort of relation there. And what we want is something like this. The semantic web would say, okay, this resource here is a piece of software, this resource is a document, and this reference is actually pointing to the fact that this software uses this document, or that it depends on this other piece of software. This software generated this document, right? So you get the picture. This is also understandable by humans, the same as before, but more understandable by computers because we can encode what each of these relations mean and what these classes mean. We'll continue seeing a little bit more about these relations and classes throughout the lecture. So the semantic web stack, or also known as the layer cake, is depicted here. We have at the bottom things that have already been standardized, like URIs, the resource identifiers, languages like XML, data interchange languages like RDF, and up to query languages like Sparkle. Sparkle is a kind of like SQL, but for semantic web languages. RDFS to encode knowledge bases, rules, and ontologies. And I have it pointed out like circled here because we'll see a little bit more about this. And if you keep moving up, it's still in research, the unifying logics, proof theories, trust, all of the things that make up the more complex problems. And you have crypto here as a traversal of everything up to this level. Implemented, we have user interfaces and applications that are in constant evolution. So if you look at this stack, it's pretty tidy, but if you go to the architecture of the web, it's not that. There's not such a direct mapping, right? So you have all of this kind of things that map back to the stack, but you have the users that interact through HTTP, HTML, that kind of thing, through different kinds of mashup sites, and at the bottom, these things that we just talked about, RDF, web ontology languages, Sparkle, and underneath all of the resources. So what are ontologies? We've been I've been moving towards this for a few minutes already. It's ontology, the word itself, you can have you can find references in philosophy to this. It's ontology means refers to what exists, what is in existence in the world. So from computer science, from the computer science side, we can say that an ontology is a model of some aspect or aspects of the world. Another way of thinking about ontologies is the evolution of a database. So if you have a database, it's a set of facts, it's also a model of some aspect of the world, but we'll be adding much more stuff on top. First of all, it introduces a vocabulary relevant to the domain. So for instance, everything that has to do with auto mechanics, so the type of objects that you can encounter in this domain, the kind of relations, kind of classes, that kind of thing. Then it specifies a meaning or semantics for terms. So for instance, starter engine in the auto mechanics world is an engine, kind of engine that's part of the car's starting system, right? So it's the one that when you turn the key, it makes the classic sound that every car makes. Well, at least the non-electric cars. And it can be formalized by logical languages. For instance, if we take first order logic, you can say things like this. So for all X objects, objects X, if X is a starter engine, then it is also an engine, is what's being encoded here. And there exists objects Y and Z that such that the engine is part of Y, and the starting system is also part of Z, which in this case we don't continue, but it's presumably another aspect of the car or the car itself. So very, very simple ontology, so we can communicate a little bit about why they're useful. So let's consider artists, consider works of art. Artists can create works of art, that's what they do. A subclass of the class artists are the painters, right? So they typically produce subsets of works of art, which are paintings. So this subset of the creates relation then is called paints. And the same kind of thing for sculptors, right? Sorry, and sculptors and sculptures. These people sculpt sculptures. And what we're missing, the final thing that we're missing are the actual individuals here, right? So artist, work, painter, sculptor, those are classes in the semantic web lingo. The individuals are called instances, and the relations are called relations. So what can we do with this very simple ontology? So we can encode them in first order logic, for instance, or other kinds of formal languages. So for instance, for all objects X and Y, if X and Y, if X paints Y, then X is creating Y, right? That's the going up in the hierarchy. If X creates Y, then X has to be an artist and Y has to be a work of art. The same kind of thing for paints. We have the X is the painter and Y is the painting. So in fact, like Michelangelo created La Pietà would be encoded simply like a fact in a database, right? Sculpts Michelangelo La Pietà. Michelangelo and La Pietà here are the individuals, the dots that we saw in the Venn diagram. And so if we only have access to that fact or that sets of facts of that kind, we can only answer simple queries like we do in databases, right? Like, what did Michelangelo sculpt? So in that case, we would get the Pietà, or who sculpted the Pietà, and then we would get Michelangelo. So it's kind of very basic kinds of questions that we can ask about this set of data. But if we have an ontology, then you can have derivations, or what we call reasoning. Typically, ontological reasoning is the use of derivations and then answering queries based on these derivations. So, for instance, who is Michelangelo? He's an artist and also a sculptor. What is La Pietà? Is a work of art and also sculpture. Do you know any sculptors or sculptures? Yes. And in this case, only just with that fact, we know Michelangelo is a sculptor, La Pietà is a sculpture. Or do you know any artists or works of art? Yes, Michelangelo is an artist and La Pietà is a work of art. So see, here we can see that Michelangelo is both in the role of sculptor and artist. So you can ask about both kinds of things. So this is the kind of thing that we referred to when we say ontological reasoning. Of course, this is a very simple ontology, very simple language as well, but there are very powerful languages in the semantic web, and typically the balancing act that they do is between expressivity, so the power that they have to represent different kinds of relations and inferences, and scalability, which is what we are after in the semantic web. Typically, when we said one of the key concepts there was doing all of this at a large scale, because the web is huge, so you have to be able to scale. So a few remarks before we finish this section. Ontological knowledge bases can then be seen as a way to simply formalize information or knowledge in terms of individuals, classes, and relations. Relations are typically either, in many languages in the semantic web, are typically only, like we saw just now, either unary or binary. And knowledge graphs, which we've heard a lot about in the past decade or so, are special cases of this kind of knowledge base, where individuals are mapped to nodes, binary relations correspond to labeled directed edges in the graph, and classes correspond to unary, it's a typo, unary vertex labels. So facts and knowledge graphs are typically stated in the form of triples, and we'll see this throughout this lecture today, where we have subject, predicate, object, and where this kind of, we'll see exactly how this is done in a little bit, where the predicate would be either the relation or the fact that the subject is part of a class, right? And it is very common in the semantic web to assume a fixed vocabulary, something that typically doesn't change. So if you're interested in auto mechanics, it might happen that something new comes out or some sort of new knowledge comes about, but typically we can say, okay, let's freeze the vocabulary and worry about the data typically being the one that changes. So all classes and relations at least are fixed a priori.